Look at this, 23.2 seconds, 60, round robin, 15.4 seconds. On their own, these are isolated flashes of raw data, unstructured, chaotic, and essentially useless for making an informed decision. Whether you are attempting to optimize an industrial assembly line or predict the outcome of a national election, human beings cannot process infinite noise. We require structure to make choices. Statistics provides that structure. It functions as an engineered pipeline designed to capture that chaotic information and systematically convert it into a structured, actionable model. The process starts by identifying a research objective and collecting information. Next, in the intermediate phase, data is organized, presented, and analyzed to build an overview. Finally, we interpret the processed data. Here, researchers draw logical conclusions and make decisions based on the analysis. To understand how this massive engine actually operates, we have to trace the pipeline backward, all the way down to a single, isolated point of measurement. A rigorous grasp of this data architecture is the only logical way quantitative fields can justify making massive, real-world predictions from a limited slice of information. Let's clear the board and isolate a single test case. Consider one specific subject of study, like a computer running a particular operating system. In statistical terms, this specific subject is defined as the element, or member. It is the absolute foundational block from which information is extracted. Next, we identify a single characteristic of interest belonging to that element. For our computer, we want to evaluate its scheduling algorithm. We classify that extracted characteristic as a variable. We then measure the specific state of that variable. For this computer, we record that its scheduling algorithm is round robin. That single recorded value, the result of our measurement, is the observation. When you compile multiple observations taken from several different elements, you generate a raw data set. This table shows exactly how that data aggregates into a structured matrix. Each trial acts as the element, and the recorded runtime is the variable we are observing. The predictive power of a statistical model rests right here. If you fail to define these base variables with absolute precision, everything built on top of them collapses. This flowchart maps out the taxonomy of variables. The specific nature of a variable dictates the exact mathematical operations you are permitted to apply to it. The first major division encompasses quantitative variables. These represent characteristics that result in strict numerical values. Within quantitative data, we subdivide further. Discrete variables are countable whole integers, like the exact number of televisions sold. Continuous variables are measurable across infinite numerical intervals. A temperature reading demonstrates a continuous variable. It does not skip from 37 directly to 38 degrees. It exists anywhere along that precise, measurable scale. Shifting to the right side of the tree, we find qualitative variables. These classify characteristics into non-numeric categories, such as blood type or gender. Qualitative data is governed by strict scales of measurement. The baseline is the nominal scale, where data consists strictly of names or labels that cannot be mathematically ranked. Moving up, we find the ordinal scale. Here, categories possess a logical ranking, like academic grades A, B, and C. We know A is higher than B, but the exact mathematical distance between those ranks is meaningless. Next is the interval scale. Precise mathematical differences exist between points here, like degrees on the Celsius scale, but there is no absolute, meaningful 0 point. A temperature of 0 does not equal an absence of heat. Finally, we reach the ratio scale. This measurement possesses equal units and a true rational 0 point, allowing for absolute quantitative comparisons, like income or physical volume. Misidentifying a variable's taxonomy, treating ordinal ranks as if they were ratio measurements, breaks the mathematical pipeline entirely and invalidates all subsequent analysis. Once you collect thousands of observations, the raw dataset outgrows human comprehension. You cannot read a wall of 10,000 numbers and extract meaning. Descriptive statistics provide the methodology to organize, display, and summarize that massive wall of data mathematically. This diagram outlines the two primary analytical lenses used to achieve that summary: central tendency and dispersion. Calculating measures in a central tendency, like the mean, median, or mode, allows us to locate the mathematical anchor, or the dead center, of our dataset. Measures of dispersion, such as standard deviation and variance, then map out exactly how far the rest of the data spreads away from that established center point. Consider a Major League Baseball season. Over 162 games, a single player executes hundreds of individual batting, running, and pitching actions. Descriptive statistics compress an entire season of actions into a few comparable parameters. A batting average is a measure of central tendency, summarizing historical performance. There is a strict limitation here. Descriptive statistics only map the data actually in our possession. They tell us exactly what happened, but they cannot mathematically predict what happens outside of that specific dataset. That limitation presents the core challenge of quantitative research. The target group that we actually want to understand in quantitative research is usually far too massive or expensive to measure directly. We call this complete, often unmeasurable collection of elements the population. It could be every registered voter in a country, or every product rolling off an assembly line. This illustration shows the mathematical bridge used to evaluate that population, the sample. A sample is a carefully selected, measurable subset extracted from the larger group. Inferential statistics allows us to use known sample results to make probabilistic predictions about an unknown population. The mechanics rely on calculating statistical significance, defining the exact probability that our observed results occurred strictly by chance. We see this pipeline at work daily in major industrial facilities. The complete daily output of a massive factory floor represents our unmeasurable population. Checking every single bolt or microchip for quality control is impossible. Doing so would require halting the production line entirely. Instead, specific elements are randomly pulled from the process, meticulously measured as variables, and compiled into a descriptive daily sample. That isolated sample generates a control chart. It grants engineers the inferential power to monitor the health of the machinery and predict the quality of the entire factory floor without touching every product. Statistics is the ultimate translation engine. By meticulously defining variables at the bedrock level, we build the descriptive maps that empower us to accurately predict, control, and understand the unseen complexities of the real world.